Thank you for joining us for today's SIA SRC joint webinar on the Decadal Plan for Semiconductor Research, New Compute Trajectories for Energy Efficiency. The webinar today will focus on the research needs to overcome the energy efficiency constraints posed by conventional computing. Panelists will discuss disruptive innovations needed in information representation, processing, communication, and storage that are all pressing and critical to sustainable energy efficiency gains, economic growth, and U.S. technological leadership. We will hear from members of the Decadal Plan Committee, which is made up of some of the foremost leaders in R&D and engineering in the semiconductor industry, academia, and national labs. Our panelists today are Viktor Zhernov, Chief Scientist at the Semiconductor Research Corporation, Heike Riehl, IBM Fellow and Head of Science and Technology at IBM Research, Gil Vandentop, Director of Corporate University Research at Intel, Stephen Kasanaki, Senior Fellow at AMD, Carlos Diaz, Senior Director, Rob Clark, Senior Member of the Technical Staff at Tokyo Electron. The panel will be moderated by Jim Eng, Chief Scientist for Computing in the Physical and Computational Sciences Directorate at Pacific Northwest National Lab. And with that, I will turn it over to Viktor Zhernov.
Thank you, Mariam, for introduction, and hello, everyone. Thank you for joining us today. And the topic of today's webinar is the new compute trajectories for energy efficiency presented in the Decadal Plan for Semiconductors. And next slide, please. I will briefly introduce SRC and Decadal Plan for Semiconductors and the 5 seismic shifts in information and communication technologies identified in the Decadal Plan. And after that, we focus on the compute needs after 2030 and specifically consider the energy challenge and the need for new compute trajectories. Next, please. So why we need Decadal Plan, the new programmatic road mapping document that will drive all semiconductor and ICT industry. The current hardware-software paradigm in information and communication technologies has reached its limits and must change. And now we need to understand, identify significant trends that are driving information technologies and the roadblocks the industry facing. This is why Decadal Plan for Semiconductors is needed, which will transform the industry by supporting the strategic visions of semiconductor companies and motivating the brightest minds in the world to find the solution. Also, it is very important, and it will be emphasized today, we need to guide revolution of research programs, and the Decadal Plan calls for significant increase of federal research spending relevant to semiconductor industry. Next, please. So the Decadal Plan has been released on January 25th, 2021, and it calls for 34 billion increase in semiconductor R&D throughout the next 10 years. And as mentioned, there are 5 seismic shifts identified in the Decadal Plan: the analog data deluge, the growth of memory and storage demands, communication capacity versus data generation, ICT security challenges, and compute energy versus global energy production. And today, next please, we focus on the 5th seismic shift, the compute energy. Next please. And one more please. So this, no, previous please. Thank you. This chart shows the importance of information for mankind, for civilization. Throughout all history, there was very strong correlation between our ability to generate and consume information and our social economic well-being. For example, back in at the times of the Great Library of Alexandria, the total amount of information stored in the world was roughly 10 to the 11 bit, so 100 gigabit or 1,000 bit per capita. Today, we are already talking about 10 to 22 bits, and we really need to get used to the new prefix, zeta, 10 to the 21, 10 zeta bit in 2018, or 1 trillion bit per capita. So while we're talking a lot about population growth, in fact, from 300 BC to today, the population growth was only 80x, 80 times. And it would be flat on this chart, but information grew grew billions of times. So we have huge amount of information per capita, and this have been the social economic growth engine of civilizations since its very beginning. Next, please. This is the next slide is in another angle. It's computing angle. So yes, we consume more and more information, and this information translates into higher standards of living. How we start all this translation? All this translation starts from elementary binary transitions. And we, as semiconductor industry, know very well how to do this part. So I would make a claim that actually all computing has been started and driven at the first period by physicists. So they invented the binary switches of different forms, and we utilized for computation. So on the level of binary transitions, everything is very simple. We just moved the ball back and forth between 1 and 0. So we create binary transitions, which we counted, and in 2018 it was 10 to the 35 bits used for computation per planet. Inside of a computer, inside of a computing chip, these elementary transitions in certain, I would call it magic way, are translated into computing instructions, which we measure in instructions per second, millions of instructions per second, MIPS, or in zeta, instruction per second, 10 to the 21, instruction per second in floating point operations per second. So there are different metrics to measure the compute performance on the instruction level, but all these metrics has a relatively simple conversion between the units. And now these computing instructions, of course, result in new computer applications, which eventually affect economic and social well-being, result in higher standards of living, and bring trillions of dollars in the world's economy. So just think of it. We convert bits into dollars. And please, Mariam, click one time. Please click, one click. So what drives this conversion, to complete the loop of conversion, Mariam, next, please. Yeah, well, please, one back, please. So, sorry for this, but yeah, thank you. So in order to facilitate the binary transitions that results in all this chain of events, we need energy. We need to supply joules to the binary transitions. And again, we can account for all energy of energy. And in 2018, it was 10 to the 18 joules used for computation worldwide. So we in the end, we transform joules into dollars and higher standards of living. Next, please. And next, please. And this takes us to the topics of today webinar: how we effectively convert joules into binary transitions and then in MIPS and dollars. So we will be talking a lot about compute trajectories. So we define the compute trajectory here as the way in which we convert binary transitions in compute instructions. So how we convert bits into MIPS and ZIPs and flops. And the related question is bit utilization efficiency in computation. What is the number of single bit transitions needed to implement a compute instruction? Next slide, please. And this is maybe the main point of my presentation. So in order to put our arms around the question how we convert bits into MIPS, we just took all published data for all microprocessors for CPUs from 1971, the first Intel processor through the current, and plotted the algorithm performance in instruction per second as a function of their binary throughput. And the binary throughput, of course, can be calculated as the product of the number of transistors per chip and the clocking frequency. Once again, this is what semiconductor industry makes very well, making smaller binary elements, smaller transistors, run it at a greater frequency and increase the total binary throughput, which we define as beta here. And now, of course, we have data on instructions per second, and when we plot instructions per second as function of binary throughput, we got certain line, which certain data set that can be extrapolated with a power function with amazingly strong correlation, almost 100% correlation. And this power function, so binary throughput is power of instructions per second, occurred to be power function of binary throughput with exponent p very close to 2/3. And why 2/3? We don't know. This answer we need to answer. Why 2/3 and how we can change this exponent. But as we will see soon, this what now is critical to getting to the new, more energy efficient computing. Very simple formula is on the bottom of this slide. The electric power used for computation is pretty much a product of the binary throughput, so number of bits, binary iterations per second times energy per bit. And as a physicist, we understand very well how low the energy per bit can be. Next slide, please, Mariam. Yes, so this analysis has been done long ago by SRC and Intel colleagues, and of course, there are different versions of this found in the literature. But in short, any binary switch can be represented by one barrier diagram, and the barrier height separates two states, 1 and 0, and the energy barrier height defines the minimum energy operation, and the barrier width, the smaller size of the binary switch of the transistor, therefore the total density of the transistors we can have. And of course, for better energy efficiency, we want this barrier height to be as low as possible, but when it is too low, the spontaneous our barrier transistors will be started due to Boltzmann thermal excitations, which defined with classical Boltzmann formula. And if we define the loss of information as 50% of error probability, we immediately can solve this Boltzmann equation and obtain that minimum energy per bit operation is KT natural log of 2, which is known as Shannon von Neumann Landauer limit, and is approximately negative 21 joule at room temperature. And also, of course, we can continue this analysis and apply Heisenberg principle that is manifestation of tunneling, quantum mechanical tunneling, and we can calculate the smallest size of the binary switch where we lose the state. Again, we have 50 probability of of tunneling transition, and it gives us roughly 1.5 nanometer size. And it takes us to the next slide, which shows how are we doing with energy per bit in CPUs. So once again, we put all data for all CPUs from all times till now, and we are doing pretty good job in this, as you can see. So the energy per switching event in CPUs is getting down exponentially, due to scaling, due to smaller device size, and due to decrease of the voltage. So we scale both size and voltage. We decrease the capacitance, we decrease the voltage. CV squared over 2 is going down. And today we are at roughly negative 16, negative 17 joule per bit, which is great. But once again, the limits are anticipated, and at some point in time, not far from now, we are going to reach these limits. So we understand the energy per bit very well and how far we can go with this. And now let's put all together. Next slide, please. So we have total computational inventory. What is the total compute performance per planet per year? And with our power formula, we know how instructions per second are related to bits per second. We can calculate total bits per year. And as I mentioned, this year, in 2018, we had 10 to the 35 bits. And now we know energy per bit. Next, please. Great. So from the word installed computing capacity in MIPS or ZIPS, we can calculate total bits, and we know energy per bit, so we can calculate the total energy of computing. And it takes us to the next slide, which looks scary, but we don't need to be scared. So this slide shows several projected lines of total compute energy used for computing in joule per year, and related to the world's energy production, which is the yellow line on this slide. The world's energy production grows linearly. The energy used for computing grows exponentially. So sooner or later, we can expect crossing the two lines. So the current line, the orange light on the slide, was obtained assuming the energy per bit negative 16. It is of course, we as industry working very hard by improving energy per bit operation. This is arrow 1 on this chart. And depending whom you ask, we can go as low as negative 18 or negative 19. But as you see, it will not help. It helped a little bit, but still we cross the energy line after 2030. Even if we are super smart and operate at the physical limit of binary iterations, so negative 21, Landauer limit, we still will be crossing the yellow line. And the point here is that why we are having this line, because it is the way we translate binary iterations into instructions per second. So these trajectories are defined by this power formula with existing trajectory P equals 2/3, or roughly 0.6566. Why it is 2/3, again, we don't know. But if we could increase it only 30% to say P close to 1 for discussion's sake, it would immediately take us to another trajectory, new trajectory with million X improvement of energy efficiency. So as we reach the limits of decreasing the energy per bit in transistor, it's time to think about how we utilize bits for computer instructions and increase bit utilization efficiency. Next slide, please. And please, yeah, how we get here is, please go back for a second. Thank you. So how we get to this trajectory, we are not sure yet. And this is the topic of today's discussion, and especially panelists. So we invited the world's best experts in computing to present their opinions, how we can get to new trajectories. It could be in part quantum computing, in part neuromorphic, different kind of artificial intelligence engines, everything on the table open for discussion. Next slide. The next slide shows a more accurate plot similar to the previous one, where we took into account more factors, including, for example, the current coexistence of CPUs and GPUs, and we also related the model developed in the Decadal plan with independent estimates of total compute energy. And you can see that the SRC model, the green line on this slide, is pretty well aligned with independent verifications. And another difference of this slide compared to previous one, of course, economists will tell us, no, the green line will never cross the yellow because economics will not allow this. Because if we approach to the world's energy production line, energy becomes expensive, the computation becomes expensive, and we will be forced to freeze our computation, which is called here as market dynamic limited scenario. And this, based on current anticipated technologies, it will limit the world computational power as 1,000 zips maximum. Of course, we don't want to get to this market dynamic limited scenario, because as we already saw, the whole development of the civilization depends on our ability to process information. So as computing growth may be not sustainable by 2040, as its energy requirements would exceed the estimates for energy production, we need to discover new computing paradigms architectures that would get us to 1000x improvement in energy. Next slide. And once again, it is not, there is certain basis behind this call. So what we need to do is improve bit utilization efficiency in computation. And once again, this is the blue line is the current trajectory, which is driven by this two-third exponent. And if we consider hypothetical trajectory with p equals 1, we have 1 million x improvement in bit utilization. So we will using less binary transitions per instruction, and hence huge improvement in energy efficiency. Next, please. Now, question how we can get there. And this is, again, the question for all of us, and some of the thoughts will be given by the panelists. And next slide, please. So what is needed is new theory of computation. Once again, we need to fully disclose the magic converting binary transitions into computation. And the theoretical basis of computing is much less solid, less developed than, for example, the theoretical basis for information storage and communication. We don't have Shannon limit equivalent for computation. We need to work on this. Next, please. Next slide, please. And today we can, so we consider different several ways we can get to the new compute trajectory topology, moving from 2D to 3D architectures, new data representation, interplay between the logic memory interconnect triad, and new physics of computation. And next, please. And the next slide, I would like to ask all kind of to take a look and think of this after we conclude this webinar. It may be something I would like all us to think. So this represents 3 cornerstones of computing. Logic. Very often we think of computing as a bunch of logic operations, but of course we need memory and interconnect to support logic operations and computing. And in this diagram, the attempt was to represent the the energy used by three of the elements of computing by the size of the circle. So in 1990, it was logic that burned most of the energy in computing. And a lot of efforts indeed were dedicated in the past 3 decades to improve energy efficiency of logic. And today, logic is the smallest circle. But the computation energy is now dominated by memory and interconnects. Even if logic is free or virtually free or a very small amount, we still will pay a lot of energy just by moving data around. Memory and communication getting very expensive. And this is what we have in 2021. Question to all of us, to panelists and to the audience. How can we envision how this triad will look like in 2030? And what we do today to move the next triad? And it's not only relative size of the circles, it's also concepts of making computing memory, computing interconnects. So if we can merge these circles together, we expect to get considerable energy savings and get to the new trajectory. And next slide, please. And to illustrate this, I just show example from biological computation that in brain, neurons are connected with multiple dendrites, which looks like wires and without as wires, but the current work shows that dendrites are much more than wires. They actually act as mini computers, so they change their state depending on distribution of, for example, calcium atoms along the dendrites, and they activate or deactivate the dendritic trees. So this is an example of compute in interconnect and memory in interconnect. And this takes me to the last technical slide. So these examples of, next slide please, of biological computation motivated us to assess the computer trajectory in biology. We took 2 data points. One is the brain. The brain computational performance have been assessed by multiple references, and in these green boxes, more or less the current understanding of brain performance. But we also did this exercise for smallest single cellular organisms, the E. coli bacterium, and we also obtain another data point in the blue box. And if you connect the dots, we get the computer trajectory actually with exponent pretty close to 1.21, which suggests that the alternative trajectories can exist. Next thing. Next, please. And it takes me to the summary that it's paramount to restore a US leadership in microelectronic technologies and innovation. And the Decadal plan for semiconductor research is instrumental to address ongoing seismic shifts in information and communication technologies. The Decadal plan identifies the what, not the how. For example, discover computer trajectories with P close to 1. Now the panel will talk about how we can get there. And what is important to mention, and how I would like to conclude my part of the presentation, with the 2030 Decadal plan for semiconductors released in January 2021, now is the crucial time to drive the conversion of the high-level grand goals of the Decadal plan into a detailed semiconductor agenda towards 2030. And this concludes my part of the presentation. And now if we go to the next slide, and the facilitator, Jim Ang, will introduce the panelists. Thank you.
Okay, thank you, Victor. So this graphic looks, I think it's a repeat of one of your earlier slides, but with a few more details. And before we leave this slide, let me just indicate the order of play from our panelists. We'll start from a couple of background slides from Rob Clark from Tokyo Electron to describe topology and its extension to 3-dimensional computing, or computing in 3D. Then we'll talk hear from Carlos Diaz, who'll cover the data representation topic. Then Stephen Kazanaki from AMD to describe heterogeneous computing. Gil Vandentop from Intel to describe this triad between logic, memory, and interconnect. And then we'll wrap with Heike Riel from IBM to describe some of the research challenges in quantum computing. Then we'll come back for a little bit of Q&A with the panel. So first up, next slide will be to hear from Rob Clark.
Hi, thanks, Jim. I'm going to talk a little bit about how we escaped the 2D topology that we've been working under. So a modern microprocessor, take the latest iPhone chip, for instance, something like 12 billion transistors on that chip, and they're all fabricated in a single layer near the bottom of the processing of the chip. So for 50 or so years, we've been working under this paradigm where we have these basically planar devices that are arranged in a single layer on the chip. And we've reached the point now where it's become very difficult to keep making those devices smaller in terms of area. Initially, it was quite easy to scale them down. Of course, we reached challenges along the way. But now we've reached the point where shrinking the dimensions of those devices is becoming very difficult. And we're using most of the area we have available for the devices as well. So if you look at the size of a transistor, you can take the die size from a modern microprocessor. And if you do a simple calculation, you figure out that, with 12 billion transistors on the chip, they have a certain area. About 70% of the usable area is devoted to these transistors already. So as long as we keep fabricating things in a single layer, we're going to have to either keep making them smaller. We can squeeze them together a little bit more, but there's not a whole lot of area available there. What we do have is volume, though. So the escape hatch is to move into the third dimension there. And that, as you can imagine, from an interconnect perspective, if you're building everything in a single layer, that's not as efficient as if you can build things in 3D space and connect them together in 3D space either. So from an interconnect perspective, going to 3D will help us as well. And so if you do the same sort of calculation looking at the volume that's available, you find out that we're really only using about 1 to 2% of the volume that's available in the chip for devices. So there is a lot of volume available for us to expand into. So next slide, please. Let's see, Miriam.
Next slide, please, Miriam.
Next slide, there we go. So this is extending the idea of the binary switch that Victor talked about earlier. And we can do some sort of back of the envelope calculations on this and think about, well, if we arrange these binary switches in a one-dimensional area sort of fashion, the way we've been building our computers, we can see that it's very difficult to get large amounts of fan out. That's a number of connections of devices to each other. Whereas if we build into a 3D topology, we can get a huge energy savings, even at relatively low branching and fan out. We can get a huge energy savings versus the 2D arrangement of the chips. Next slide, please. So the idea is the 2D layout has served us well, but now the long interconnects result in things like the memory wall that we're having to overcome for artificial intelligence. A hypothetical 3D topology is a better arrangement overall, just in theory. In practicality, this enables us to start building systems where we can build many devices on top of each other. We can create heterogeneous systems where different types of devices are stacked on top. We can consider about feed-through processing and use our devices much more efficiently, connect them together much more efficiently with high branching and fan out as well to gain some energy and bit efficiency. Okay, now I'd like to pass the wand over to Carlos Diaz, who's going to talk a little bit more about the computation. Thank you.
Thank you, Robert. Technology improvements will need to become increasingly more significant to sustain computational capacity growth over the next decades. This is illustrated by the dark green arrows shown in the chart of the left that has the current and projected computing energy per year. Research areas to tackle energy efficient computing include material discovery and synthesis, processes, device interconnects and system integration, fabrics, compute and system architectures, such as domain-specific architectures and things like that. Artificial intelligence is a key element in the fourth industrial revolution. Increased cognitive capabilities while attaining 100x or more power reduction will be critical regardless of the application domain. And this challenge is illustrated in the chart at the right. As we aim towards the cognitive capabilities of the human brain, changes to the human, changes to how the information is represented and how it is processed must be explored actively to contribute necessary energy efficiency for practical next generation AI systems. And this is critical beyond those that I alluded before regarding the conventional compute energy efficiency improvement knobs. Next, please. One such new type of representation is based on high dimensional vector spaces. In conventional computing information is represented by binary vectors of low dimension where the value or a meaning is contained in the bit pattern itself. In high dimensional computing, the information in contrast is represented by relations between the vector patterns, with each vector being of very high dimension itself. The error tolerance of high dimensional representations is higher than conventional representations. The figure in the center from a research work on the subject illustrates that feature. And it shows that high dimensional computing retains the accuracy despite up to 10x increase in the memory failure probability. Similarly, another feature of high dimensional computing is the opportunity for it to scale better with the problem size. And the table on the right illustrates that for a particular AI application in language recognition. And that illustrates that how high dimensional computing scale much better with an index of the problem size as compared to a traditional baseline. And here size being a measure of the memory capacity required to support that problem. Therefore, high dimensional computing can significantly enhance AI's computing energy efficiency, given its intrinsic one-pass and continuous learning capabilities, the error robustness, better scalability features compared to, for example, deep neural networks. As Victor mentioned, also, there are other types of representations that are exploit the time sparsity and the signal and the timing between signals and the signal shapes themselves that are exploited, for example, in spiky neural networks. So, there are several types of information representation that really need to be actively explored and that will fundamentally contribute to the energy efficiency improvements that we need to attain in order to continue to grow the computing capacity and satisfy the demand for next generation AI cognitive capabilities. So with this, Steve, please take it over.
Okay, thank you. So here I'd like to talk about the changing of the computer energy trajectory and how heterogeneous processing comes into play. The chart on the left, Victor outlined earlier, and it nicely shows the worldwide aggregate performance and demand for instructions per second. And it's increasing at an exponential rate. And there's really no signs of it relenting. It will keep, the worldwide demand keeps going in that direction, driving our economy. And on the right, Victor showed on the first slide in the CPU, the brown slide, or the brown curve there in the right slide, that shows the total number of bits per year switching as a measure of energy. And here I've outlined kind of a limit here where market dynamics will start to take its toll here and start to limit the total number of bits per switching capability due to worldwide energy limits, and as Victor outlined earlier. And one of the things, reasons for this limit in that trajectory is in that rate is that the CPUs, the general purpose CPUs that we've been using for many decades now, really have been optimized to process kind of the scalar programming code that is written, and it does a really good job at that. And what it does is it spends a lot of switching and energy extracting intrinsic parallelism in that code to make it run faster. And by doing that, it's really tailored for processing single threads or a small number of threads at very high speeds. And it takes a lot of energy to do that. About a few decades ago, a new class of processors started to emerge called GPUs, or graphics processors. And the GPUs were optimized for processing explicit parallelism in a scene on your computer screen, where you can do a lot of this in parallel. And so a lot of the architecture was geared for not extracting internal parallelism and optimizing that, but for letting the software hand it externally parallel processes that can then be done at orders of magnitude more parallel than in a CPU, in a general purpose CPU. And by doing that, you can see the trajectory of the GPU actually has a smaller trajectory in terms of the total number of bits for switching to meet the global demand here. And as the industry embraced that about a decade ago in terms of uses for high performance computing, HPC applications, you can see that it tilts the curve down a little bit more and extends out a little bit further in the future our limit to reaching our limits in computation due to energy limits in the worldwide worldwide. The next area that shows a lot of promise is taken from examples of like the mobile application processor or various application processors is a class of architectures called domain specific, where the architecture is really geared for a specific domain of applications. And here, much like in the GPU, the architecture can be optimized for a certain class of algorithms. And then that, in combined with the CPU and GPU type of processing architectures, we could further potentially tilt this curve a little bit further down and get more years and to meet the demand of total worldwide compute. And then eventually that will run out of steam, and we will need to look for other types of approaches, as mentioned from the other speakers.
Hey, Stephen, this is Jim. Let me just interject that I think the R&D opportunities as we explore new models of heterogeneous computing actually will have a benefit in two ways. One, in the software stack, meaning the runtime software, the programming models, the efforts to decompose applications into these different elements that make up the heterogeneous computing processor. And then the other is actually where this software infrastructure and the way of you thinking about the software stack also applies to how application developers think about their workloads and how the maybe the different tasks within their application might map to different processing elements. That thinking hopefully should be transferable to new paradigms of computing that are introduced with accelerators that, as you say, are domain specific or more specialized, but that's an on-ramp to quantum computing or neuromorphic computing.
Mm-hmm. Yeah, thank you, Jim.
Yeah.
And I'd like to also add to that comment here is where in much the same way the GPU, the graphics processing and the graphics coders learn how to program a GPU. The scientific programming models adapted to work with a GPU type architecture, more parallelism, and writing in that explicit parallelism up front in software and removing that burden by the hardware to make it more efficient. And with that, I'd like to hand over to Gil.
Right, thanks. Next slide, please. So yeah, I got assigned the architecture hypothesis, and both Jim and Victor know I'm a chemist, so I'm not. I think I missed a meeting, so I got that assignment, but that's okay. I thought Victor did a really nice job of describing the problem and the opportunity, right? I mean, sort of the urgency of the issue looking forward, and then also the opportunity. I mean, a million times gap between those two lines, right? And nobody knows why we're stuck on P equals 2/3. So I thought maybe I'd ask the audience, if anybody knows, please put the answer in chat, because that will help us out a lot, because none of us know the answer. I'm gonna argue that our best hope is new architectures for compute in memory or compute in interconnect. Going back to some of the descriptions that Victor made around the brain, right, and the way the brain works, because we know it does some combination of compute in memory or compute in interconnect. We know it's a lot more efficient than what we can manage, but we haven't figured out a way how to architect those systems into silicon. So I think there should be a way there for us to make some significant advances. I mean, there's been a lot of work over time on compute in memory, maybe not as much in compute in interconnect. We haven't had an efficiency breakthrough, but I think we just need to invest more. I put the center slide in because we didn't really emphasize device options, and I don't think more efficient transistors are really going to get us off the P equals 2/3 line, right? I mean, but it'll continue to help us, move forward. So we need to continue working on fundamental device work, mainly because it takes a long time, and it also takes novel materials to support that device work, and that also takes a long time. So investments there are also very important. I actually think the most likely thing to get us off P equals 2/3 is probably quantum computing. I think it's probably going to take too long. So I'm excited to hear from Heike about how the progress in quantum. Over to you, Heike. Oh, you're muted.
Yes, exactly. I need to unmute.
Okay.
Yeah. So thank you very much. Let me see. I got some thing here, some Zoom message, but I hope it. Can you hear me?
Yes.
Okay, perfect. Yeah, I think I want to talk about quantum computing. It's kind of the new kid on the block here, and has the potential of changing the game because of it's a completely different computing paradigm. Instead of bits, it uses quantum bits and uses the laws of quantum physics to calculate. And for certain problems, this really makes a difference. It exploits the laws of superposition and entanglement and interference. And thus it can create with the number of qubits really the potential of an exponential increase in performance with the number of qubits. So you can create 2 to the power of n basis states, and due to the exponential law, you immediately increase the number of the dimensional space you use for computation. And that's fundamentally different to the conventional computing, and therefore the quantum laws can enable the exponential increase. Of course, it's a theoretical basis, And thus also it can enable the degrees of energy use. So if you look at the middle here, then quantum computing is built for difficult problems, and it's built for certain problems where the complexity exponentially increases with the number of parameters, but there are still problems which also quantum will not address. So there are these big square which problems we can't address adequately today. But of course, there are problems we can solve with our computers today, which are, for example, not normal multiplications. But the problems we can address with quantum computing, and one famous example is, of course, factoring big numbers. But there are more, and these are also currently explored. As I mentioned, these are specific examples where the problem exponentially increases with the number of parameters. This could be the simulation of quantum systems, which appear in physics, in chemistry, or material science a lot. Algebraic problems, for example, machine learning, differential equations, factoring, but also in database search, where quantum can make a difference. This is, for example, for optimization problems or quantum Monte Carlo and others. On the right-hand side here, I show you a bit where we stand and where we go. And so when you look at the upper graph, you see on the y-axis the number of operations, which we also call the circuit depths in quantum computing. And on the x-axis, the circuit width, the number of qubits. And as you can imagine here, we are currently kind of in the lower left corner, but we want to go in the upper right corner. This means today, the number of qubits are in the range of about 50 to 100. And the circuit depth is also limited. And we're working in the technology to increase both of these numbers to not only look into toy problems, but to solve real problems with small quantum processors. That's the green part. And this will be really becoming very interesting in the next couple of years, where the 1,000 qubit barrier is reached and planned to be reached in 2023. And then, of course, if you want to go for universal quantum computing, then you need to reach millions of qubits. So there is a new path to solve problems which can even not be solved with classical computers. And of course, let's move to the next slide, because we want to look at what are the potential benefits in performance and energy consumption. And so on the left-hand side, I show briefly the Shor algorithm, which is a very famous one, which needs also a universal quantum computer to be solved. But it shows you the big benefit quantum computing can bring. Because here it's proven in the sketch here, where you see the number of operations for factoring. And the red line is for the best classical algorithm, and the blue line for the Shor algorithm. You really see the exponential speed up for factoring what quantum computing can bring. And this means a task which may take like 300 years on a classical computer might take only 30 seconds to a minute on a quantum computer. And this, of course, has then the big potential to lead to the speed up as shown here, and also to a reduced energy consumption. However, the energy consumption part is not fully proven, because you need a universal quantum computer. This means you also need error correction. And there is currently research going on in order to figure these things out. But a few recent examples I wanted to show you here in the middle, where calculations on a real quantum computer have been done. The first example was done on a 53 qubit. It's an artificial toy example, which was calculated by measuring the probability distribution by sampling computational state space of dimensions 2 to the power of 53, where 53 is the number of qubits. And actually in the first bullet, you see that on a quantum computer, it took 200 seconds. And actually here I made a mistake, because it's 2.5 days on a HPC, or about 200,000 seconds on an HPC. And if you then calculate roughly the energy, then this would mean also a big difference between the quantum computer of 5 times 10 to the 5 joule, versus 3 times 10 to the 12 joule. In the second example, this was an example where a photonic quantum computer was used, and again, also a toy problem, which is boson sampling, where exactly, of course, this photonic quantum computer is the right tool to use. This was done in 20 seconds with 76 photons implemented in this photonic quantum computer. and it would have taken like 6 times to the 10 to 8 years on an HPC. The last example here, the third one, is on simulations of a hard random quantum circuit where 2 HPCs, Electra and Summit, were compared to a true quantum computing unit. And here you see the megawatt hours difference, and this was published by Villalonga just last year. So you see there are big differences, but there is more research to be done, and because in these calculations, not everything is considered. For example, in example 3, or in all these examples, error correction is not included, which provides further energy overhead. But there is also potential to further reduce power by integration of the electronics. Algorithms, of course, are important. And therefore, I've shown you this picture of this full stack here on the right-hand side, where you start with the physical quantum processor, the controls readout, the quantum error correction on top in order to get your logical quantum processor. But then also, of course, the quantum algorithms, how you implement it, and all this will also influence the energy consumption. So there is further understanding and work needed to benchmark, but there is a tremendous potential to save the energy. Yeah, so with this, I give back. I'm done. Thank you.
All right, thank you, Heike. Let's move on to the next slide. That's our first discussion question for the panel. And maybe I'll preface this by talking about within the Department of Energy, how a lot of our interests have shifted from just pure, extreme scale, high performance computing to solve scientific simulation problems to what the Department of Energy calls AI for science. And in this, we're thinking about how high performance computing systems will evolve to really cover converged application workloads. They touch on the heterogeneous computing that Stephen was describing, where the challenge problems are traditional modeling and simulation of physical simulations, but they're augmented with artificial intelligence and machine learning and other forms of data analytics. And that is the computing that might happen in a supercomputing facility. But then that facility is also integrated through the internet to a large collection of DOE's experimental facilities where a lot of the experimental data is collected. It may have the benefit of inference engines or streaming analytic filters to work in real time with the raw data that's collected at instruments and sensors. And this gets pooled in part of a rich data ecosystem where supercomputers are integrated with these experimental facilities. And so that's kind of the challenge problem that the Department of Energy is looking to for the next decade or more. And my question then for our panel would be, how is the R&D called for in our decadal plan going to impact future energy efficient computing solutions that are applicable across a diverse collection of applications? And maybe for that first question, since Gil mentioned his background in chemistry and materials, I thought maybe he could give his perspective as a domain scientist on applications and how that, the SRC decadal plan requests for R&D might impact that field.
Thanks, Jim. I was expecting you to ask me question number 2, but you're always good at keeping people on their toes. So good. Everything that's going on in around the country and within the government right now, right? I mean, it's a lot of it is the amount of R&D that needs to be done, right? I'm going to address kind of both questions, I guess, together, okay, right? So I mean, we went over a lot of fundamental stuff where there's a lot of opportunity, right? Actually, we even got a suggestion to the answer of the P equals 2/3 question in the chat. So Victor, you should take a look at that. I wasn't expecting that. So that's pretty cool. But there's also missing infrastructure, right? So for some of these solutions that are coming out of academia, they're not ready to be adopted by industry yet, right? And there's not really the facility to translate that R&D into solutions that are commercially viable. At least it's going to take some time, right? So I think that's really important. Is there's the money that goes into the the foundry business for manufacturing capability, right? There's the money that goes into R&D for pushing forward some of these solutions that we need. But then there's this infrastructure piece that's missing, right? And maybe that comes in the form of this National Semiconductor Technology Center, right? And that would provide the infrastructure, and then industry and academia could come together to work through some of those tech transfer issues that really, that limits. All these fundamental things are limiting us, but these practical things are limiting us too in terms of implementing new technology. So I think that's how the R&D dollars can really help solve the problem in a practical way.
Great, thank you, Gil. Miriam, why don't I suggest you stop projecting the slide so we can see the entire panel. There we go. Let's see. Does anyone else like to offer some answers to these discussion questions?
Sure. This is Steve Kawasaki. So I've spent my engineering career working on ways to make computing more efficient, energy efficient, through various ways, reducing margins and improving the efficiency overall. And actually, I like the answer in the chat. Actually, it goes to one of the points I was trying to convey, is that in our classical approaches to architecture and in computers, we had traditionally spent a lot of energy or switching, optimizing, and making up for programming deficiencies of not using every transistor precisely the amount of times it needs to calculate the problem that the application requires. And so that leads to excess heat, which is actually a very good point. And that's ultimately the consumer of energy here. And so things like moving the trajectory slightly over, making that more efficient, and pushing it backwards, and that's what the GPU really was doing, is pushing a lot of the work of parallelization back into the programming model, into the software backwards, more from the hardware, and that works very well. So I wanted to make that point there, while we had that up there in the conversation. But to make massive changes, historically, we've always seen it takes 10 to 20 years from a disruptive technological solution to really get into widespread use in products and productization. And if we come up with a new architecture, there's a huge infrastructure. A good analogy is a kind of a tanker ship, and moving, to make a turn, it takes a long time to make that turn. You have to start moving that direction if you want to. You can't move on a dime. And the same thing with the computer industry. We need to start making those changes now to get where we want to be 10 years from now or 20 years from now, and putting that foundation in that turn. And that really takes a more targeted investment in these areas of not only making the efficiency of the switching optimize that piece, but also really in everything we've talked about, the data representation is a big key also, because if you could represent the data more efficiently, that's a huge efficiency improvement. And if you could reorganize the stack using advanced packaging techniques, that's another big lever we can employ here in topology and taking advantage of that. And then also, of course, bringing the memory much closer to the processing itself is another big piece of reducing energy transactions. So all those combined, I see as the major innovations that are required to move forward. And then of course, we have quantum computing as something that we hold out. We may not be able to put on our wrist and wear a quantum computer, but certainly can maybe offset a lot of the computing needs, in the for HPC applications and things that our wrist computer may be talking to in the future.
Thank you, Stephen. I think you're also queuing up Rob to address the the 3D topology aspect. So Rob?
Yeah, I think what Stephen was talking about hits the nail on the head. I think in terms of the infrastructure we need to build in order to realize some of these ideas, it takes a long time to build it. You know, the tools we have are set up for a 2D world, and we've got to expand those into 3D, and that makes things, you know, that extra degree of freedom is huge in terms of the complexity that comes into play. And then also when we think about how we put the 3D systems together, you know, you can take disparate parts and try to glue them together. You can try to start building things in a more monolithic fashion. And it's all determined by, you know, how much interconnection do you need between these different systems, right? If you really need a lot of interconnect, then you have to build things sort of monolithically, where you're using lithographic alignment between different layers. If you can afford to go, you know, through an interposer or through some more interconnect and have maybe fewer interconnections, then you can put things that are wildly different together in new ways that we haven't considered in the past as well. The idea being that, you know, starting from a systems perspective now that people are adopting, that, you know, you can start designing systems that will do a job much more efficiently than the general purpose computing that we've been using in the past. So how we create that design infrastructure and also the manufacturing infrastructure that supports it, it's going to take a lot of work, but with the change of thinking, I think people will realize systems that are much more efficient and not suffer from some of the limits we have now with interconnect between devices and between systems.
Thank you, Rob. I think, you know, capturing these kinds of drivers, or really what are the research directions that require the sustained investment in the infrastructure, is really what this decadal plan is all about. So hopefully we'll be building support for that. Heike, yes.
Yeah, I wanted to add a bit, because I mean, there has been already touched certain points, but I think also this combination of the quantum computing, the conventional computing, and call it neurons, like these bits, qubits, and neurons, and combination, I think can bring a lot of different, I mean, really can make a change, because you have the hardware which has to interplay. You can use it with, you know, you can optimally use it for the different applications you may have in mind. And in the end, it's about how to solve a problem most efficiently. So I think we need to also think the hardware and software and workflow co-design or co-optimization. And that brings in also what you pointed out, Jim, the applications, right? The application drivers, they may require different solutions for different applications. And of course, when you look at the decadal plan, I think there are lots of fundamental questions which need to be solved and which demand fundamental research. You can consider, I mean, the 3D, building in 3D on a nanoscale, right? Knowing where each atom sits. I mean, that will become also important for certain applications in quantum computing. New topological effects, which are discovered, where discoveries is ongoing, can bring on also further energy efficiency. I think this fundamental research with applications in mind, and also in the AI hardware, there is what's done is kind of using conventional transistors with a new architecture, but you can think more, and Victor mentioned it, right? We don't understand the brain yet. I mean, there may be more behind which we need to discover in the future. New materials, new devices in a new device architecture may require then also different level of interconnects, 3D fabrication. And I think there's really a rich set of very, very difficult things to solve. And so I think there is, we won't get bored the next couple of years.
That's right, that's right. Carlos, let me bring you into the conversation as well, because you've been you know, a proponent for high dimensional computing, and primarily your use case is driven by energy efficient AI. But I was wondering if you could make some projections on how high dimensional computing may also be useful for for other application areas, or maybe the integration of AI with like in my case, scientific computing or other application drivers?
I think primarily high-dimensional computing from the space, the algebraic space it represents and the operations it constructs is trying to really take on, the challenges of next generation AI, the cognitive capabilities such as reasoning and things that could, in principle, be done by existing state-of-the-art deep neural networks, but at the expense of energy and power that make them perhaps not that practical. Right? So that's one type of representation that I believe right now primarily look at it from the point of view of AI applications. Now, in terms of scientific computing area, I think how to map some of those problems into high-dimensional representations and utilize that to do a smart search of materials or devices or designs of systems. That's in itself a tremendous field that need to be tackled. So I think the opportunities are there. And the point here is we really need to keep looking out of the box, right? And that's why, when we talk about conventional computing or when we enter a new stage of certain particular application or concept becoming mainstream, at some point, that might saturate in terms of the opportunities or the difficulties to conquer the next level of expectations. And for that, we might need to take a step back and say, look, is there any alternatives or anything that we really haven't touched? And I think, alternative ways of information representation and how they get processed are very critical to research on as we try to tackle these energy efficiency challenges that we lay out at the beginning. And I might add to this one that I believe is extremely important that the research investment is, first of all, balanced and spread out all the way from the materials and processes up to the system architecture, software, and new information theories that will allow us to carry forward over the next 2 decades. And like some of you have mentioned, from a concept to prove the concept and actually to eventually figure out which concepts made it into really a practical production capable feature, it takes years, if not decades, right? And therefore that balance investment, I think, again, from materials and process all the way to system architecture, information, technology in general, need to be there. If we look at the history of the technology, there was a time where, CMOS, when CMOS came over, the energy efficiency was there, and then the technology carried on, not to know the energy efficiency improvement with significantly. But as recent as 2000, or, it started in 2000 or in that time frame, it was necessary for circuits and to begin to step in, and we start talking about power management and all things. And then now system architectures need to get involved. And in the end, what we're trying to make is that find out what are the hottest spots where, the bottlenecks are either in speed or in power consumption, and tackle that. And that is spread out through entire hierarchy. And therefore, even at this stage today, with efforts again from technology to system architectures, everybody contributing to that. That's why we have what we have today. If we haven't done there, we couldn't have or enjoy the things that we we enjoy today in terms of portable and computing capability in general. But going forward, now that we are there, that everybody has tried to tackle those bottlenecks, I think going forward, then research really need to be, research funding and research efforts need to be first really uniformly tackled, again, from the very basic building blocks all the way up to the final systems. That's critical in my mind. The other part that is important for research, I believe, is that as we explore new concepts, researchers we all need to keep in mind a holistic set of metrics. I need to know my new device concept. Okay, I'm claiming it has a certain amount of performance or potential, but then how much of that actually will pan out when it's part of a bigger system, right? And there are need for tools for modeling capability to understand when we put all together, how much that will benefit ultimately. And that actually is extremely important also to be able to, start from a very broad set of solutions and options that there might be, and then how to net them down and be able to wisely focus the research funding as things begin to mature, and things will come off because they are fundamental roadblocks, so they might need to stop. There are others that will continue to move forward, and that's a long way to go.
Great, thank you, Carlos. I know based on whatever all of you have said, I have a comment I'd like to make, but before I do that, I'd like to invite my fellow panelists to see if there are any reactions that they would like to share based on what your colleagues have said.
Thanks, Jim. I wanted to kind of pick up a little bit more on Carlos, whatever he was talking about neuromorphic computing, and I think one of the key challenges here is, as this field evolves and the applications mature in neuromorphic and AI, we will need more targeted architectures and device technology itself to better implement those, as Carlos was mentioning. Because right now, we've been trying to do all that work in mostly software on conventional processors. And some companies, some organizations, demonstrated some novel approaches there for neuromorphic processing, but those are still difficult to program. The easiest one's still on more conventional, and I think that'll work for a little while. But to go to the next level really could require a fundamental kind of examination of everything from top to bottom, from technology, the switching, and application, data representations, everything.
Right, very good. Anyone else? The comment I wanted to make was really that as we're ending Moore's law, and I know there's still a debate. Some people say, well, Moore's law is still healthy, but if you accept that it's slowing, I wonder if the semiconductor, microelectronics community, computing community needs to rethink how we view time, right? That instead of saying, well, you always need to be preparing for the next processor tape out that is 18, 24 months out, we shift from a focus on technology development to this maybe longer term focus on research. And as a community, I don't know that we've come to grips yet with the need to make this maybe change in how we view time. I don't know, but that was kind of a recurring theme that a number of you had said, that we need to be taking a longer view, and making these focused but longer term investments in R&D. Comments?
I think, Jim, trying the cadence of the technologies will be there, and time is of essence, right? Mm-hmm. And it's of essence because, again, the current state of the art technologies will, there's a tremendous amount of innovation, little by little, making the bars increasingly higher for any alternative technology to come along, right? So research, in research, like in development, like everywhere else, time is still of essence. Mm-hmm. And that's why, I believe these research efforts across all levels of the hierarchy are very critical, and they need to be comprehensive, and they need to, really be able to look up and down in the stack and see how do they complement each other. And if we can achieve that collectively, I think we'll figure out what really the next breakthrough might be. And some of those may be just, there may be just a breakthrough, or maybe just, even though it's a new feature, a new functionality, but then that put together with an existing, well-matured, well-refined solution, take us to the next level. And I think that's the path forward.
I think, Carlos, you're raising a need for these multidisciplinary teams so that when a breakthrough is made in a specific technology arena, the community knows how that gets implemented, what its repercussions are on, for example, an advancement in materials that leads to a new circuit design. What are its implications on new algorithms? So, yeah, others.
Yeah, Jim, I think we need to do both. There was a comment, I think from SETAS, that there's also workforce challenges, right? And that there needs to be a certain amount of excitement in academia to bring in the top students to be focused on these hard problems, right? So I think that underlines your suggestion, right? I mean, we can work hard on our short-term cadence, and we have to, right? Mm-hmm. But if we don't do the longer-term research, right, and attract the students that we need, we're not going to be able to meet the demands we have for talent, right? So I think that was a good point in the comment, that we need to do that investment for multiple reasons, for the students and for the long-term technology health.
That's Jill. That's a very critical one, indeed. Yeah, tremendously important.
Gail, that's a very good point, because right now, there's a lot of excitement for AI and machine learning, right? But we have to understand that it's only going forward when the compute power is there and the energy consumption is reduced, because that's a prerequisite for the rest to work.
Yeah, and the new students are all gravitating, in that direction, in the AI and software direction, and we have to somehow revitalize, and quantum, yeah.
One of the things I think Moore's law, as driven by Dennard scaling, in semiconductors, really was a blessing and a curse at the same time. It allowed the whole compute industry to continue to scale and improve energy efficiency, but then it also kind of drew away a lot of R&D in other areas. Because you could just wait, and next generation computer would be that much faster, so you don't need to do anything there, right? And I know that, having worked a long time ago on stalk arrays for neural processing back in the late 80s, early 90s. It was one colleague once told me, Steve, why are you doing this hardware accelerator? You could just wait 2 years and buy another processor, and that's the truth. But if that's not going to happen now, we need to do something different now. And I think that'll help drive the students and the research naturally because of this end of the scaling limitation we have.
Yeah.
I think Stephen, I'm sorry, Jim. I think Stephen, that's a very good point you bring up, because I think that's also a point which goes to where the funding comes from, right? Because if a roadmap is provided, then it's easy to fund the roadmap because you have a good prediction of what the return of investment is from your funding. But if you go into unknown territory, which is required in some of these areas because it's not predictable whether this will be the solution, it's more risky. And I think that also is a required understanding needed from the funding, that to some extent there needs to be also like more risky things, which then can also bring more gain in the future.
Let me just interject. I know there have been a lot of inputs on the Q&A line. Victor, I'll ask you if there's one that you think we should focus on here as a panel right now, and then I'll assure everyone online that as a group we will be providing responses to all the inputs.
We received quite a few very good questions, and I also personally appreciate input on the two-third exponent. So we got some healthy, good, useful input. So what we will do, good thing about this virtual webinars is that we promise that all questions will be answered and sent back to the audience. So in the interest of time, there are questions very technical. I a little bit hesitant discussing them, especially as panel. There's one simple question which I just read. So can speakers highlight which project questions were impacted or driven by US government federal funding? And I'll start answering it, and Jim, as a representative of government, may add, or everybody. So I think the Decadal plan is intended to help US government to define new research directions. So it is not that Decadal plan is impacted or driven. It is that Decadal plan impacts the future funding. So Jim, can you add to this something?
Yeah, I guess I will certainly cite that the Department of Energy and the National Science Foundation have made significant investments in quantum information sciences research centers. In fact, Heike, I don't know if you realize, but I'm actually involved in one of those research centers with IBM. There are also significant investments historically that the Department of Energy and our DoD colleagues have made in advanced architecture, R&D. Some of those are already now going to see fruition in the first generation of DOE exascale computing platforms. And those were investments in interconnection networks, analyzing advanced memory concepts, and maybe the modification of GPUs to make them more suitable to scientific applications. Those kinds of investments involve many of the US computer companies, and they also set forth a lot of collaborations between the DOE computational scientists and algorithm developers, and then the counterparts in industry. And I think those types of co-design collaborations are a lesson learned that will be carried forward into the future. But the rest of you, you have thoughts on where federal investments have impacted your companies or technologies? So
if I may make one comment now, organizationally, since we have only 2 minutes left and we need to give Miriam a chance to wrap up, I just say that, again, thank you for all questions, and we'll answer them all. Please allow us 2-week period to answer them, because there's certain communication protocol how we'll collect the questions, and we discuss them as a committee and always assign some questions to different people. But within 2 weeks, all questions will be answered and communicated via SIA website. Sarah and Miriam will be taking care of this communication. And now, Miriam, I think it's time for you to say.
Yes, I just want to thank all the panelists for joining this joint SIA SRC panel. For those who want to see this panel again, it will be posted on the panel website as a recording where we will also answer all the questions. We also encourage you all to visit the SRC website to read the Decadal plan. There is both an abridged version and a long in-depth version. If you have any follow-up questions, please reach out to SIA or SRC. Thank you.
Thank you, everyone.
Thanks, everybody.
Thank you, everyone.
It was fun.
Bye.
Thank you.
Thank you.
Take care.
Thank
Bye-bye.
you.
Thank you.
Bye.